Hello, everyone. Welcome to this week's Applied AI seminar series, where I'll be talking about utilizing Raytune for healthcare AI applications focused on optimizing chest X-ray classification. So just to give an introduction, AI in healthcare is revolutionizing diagnostics, treatment planning, and patient care. It's important to tune hyperparameters to get the very best model possible. So this is critical for model performance. It can be time consuming and complex though, because typically you'll have a grid of hyperparameters that you can explore. And the most naive approach is to actually iterate through the full grid of hyperparameters and find the one that best works for your given data set. This can be improved on by utilizing tools like Raytune, where you can use efficient, scalable hyperparameter optimization utilizing Bayesian techniques to find the best set of hyperparameters. So the challenge that we're going to be focusing on today is automating pneumonia detection from chest X-rays. So we're using the chest X-ray image data set, which contains a number of pneumonia and non-pneumonia data sets or entries. So there's basically two categories. There's different types of pneumonia versus non-pneumonia. And we're going to optimize a deep learning model for high accuracy and reliability, with the goal of demonstrating Raytune's capabilities in a real-world healthcare application. So just to give an overview, Raytune is a distributed framework for model selection and hyperparameter tuning. It utilizes parallel execution across multiple CPUs and GPUs, and you can utilize early stopping of underperforming trials to optimize the hyperparameter search. You can utilize flexible search algorithms, you can use random search, you can use Bayesian optimization, etc. So Bayesian optimization is typically the best way to go just because it'll reduce the hyperparameter search to a space that would be optimal for your given training set. And it seamlessly integrates with PyTorch, TensorFlow, and other ML libraries. So just to go through some of the code, I have an example that I'm going to be sharing with everybody. But part of the first step is setting up the environment. So here we're just setting up the Raytune imports utilizing Raytune and schedulers for actually scheduling the training. So we set up the imports and we set up the data transforms, and then we can actually define the model architecture. So here I'm using ResNet 18 with two classes. So I'm just pulling a model off the shelf. So ResNet 18 is a powerful convolutional neural network. We've used this in the past for this data set and for other data sets during these seminars. You can actually pull pre-trained weights to improve the training for this. So potentially utilizing pre-trained weights can reduce the number of iterations to convergence. But the main point is we're utilizing ResNet 18 for this particular task. So here we define the training function. So basically we have the model, we have the optimizer, and then we're looping for a number of epochs for the train and test phase. And we're utilizing Raytune's tune.report report for logging metrics. It handles both training and validation phases, and this can seamlessly adapt to both CPU and GPU-based training. So it's a very relatively flexible code that can be implemented across different architectures. So we can actually configure the hyperparameter search space as well. So here I'm just defining a dictionary of the different hyperparameters that we're utilizing. So we're utilizing the learning rate, the momentum, and the batch size. And within Raytune, we can use log uniform, or a specific list of hyperparameters to choose. So with log uniform, it's going to explore this range in a log uniform way. For uniform, it's going to have an evenly spaced list. And for choice, it's the actual list that we provide. So we're going to optimize this full space utilizing a Bayesian optimization-based approach. So we're utilizing the ASHA scheduler, which stands for Asynchronous Successful Halving for efficient early stopping. We're going to be specifying the number of CPUs and GPUs that we use per trial. And we're going to adjust the number of samples and epochs for this given trial. But the main point is this is a pretty simple add-on to the original code that we had. You just need to set up the scheduler, the tuner, and specify the parameters that you'll be tuning. And then to run the actual hyperparameter optimization, we basically just use tuner.fit and we collect the best results. And then at the end, we can print the best trial configuration and the final validation loss and the validation accuracy for the best set of hyperparameters. So you can also plug this into TensorBoard, which we talked about last time. So you can view the results live via TensorBoard. So some of the advantages of utilizing Raytune is it's efficient. So you can do this with parallel execution and early stopping. You can have faster discovery of optimal models. So instead of hand choosing a set of hyperparameters by looking at the loss curve, you can actually set a grid of hyperparameters and have the best models discovered automatically. It's also very scalable. It handles large data sets and it works with computationally intensive models. And it's also reproducible. So if you set the random seeds at the beginning of the code, you can have consistent results across different runs and environments. Some of the challenges and considerations to take into account, however, are there can still be long training times. So especially when working with imaging models, these type of models often require extensive computation. You also have to balance exploration versus exploitation. So you want to find the global optima. However, you want to make sure that you're doing this in an efficient way. And when you're training any type of model, you want to ensure that you're training it on a safe environment, which is why working on the CHPC is a great place for this, because we're a HIPAA compliant resource and you can train models like a Raytune type optimization on our systems pretty easily. You also have to take into consideration overfitting. So you want to utilize cross-validation strategies to make sure that you are optimizing the model over n different folds, but that can also introduce time cost and computational cost. But if you want the best model, I would recommend utilizing Raytune with cross-validation. So some of the best practices for tuning these models are to start broad and then refine. So begin with a wide search space and then narrow down in subsequent runs. You can leverage some of your domain expertise as well. So you can incorporate your own knowledge into the parameter selection. You want to be rigorous with validation, so use cross-validation techniques. And you want to monitor the computational resources that you're utilizing. So you want to have a balance between the exhaustive search and the practical constraints. So in terms of future directions, I would say that you can utilize the code that we're providing as part of this seminar to begin your own work with Raytune. You can utilize adaptive search strategies to solve your specific challenges, and you can do multi-objective optimization. And you can also utilize this within the context of federated learning, where you can tune models across distributed healthcare data sets. But this is a starter code that we're providing, which goes through some of the basics of loading model off the shelf, utilizing it for finding an optimal set of hyperparameters, and then exploring the metrics from that optimized model. So in conclusion, Raytune is a powerful tool for optimizing healthcare AI models. It can demonstrate effectiveness in terms of optimizing classification tasks. There's a lot of potential to significantly improve medical image analysis and diagnostic accuracy by utilizing tools like this. And I would just emphasize, again, responsible and ethical use of AI for healthcare applications. So train on resources that you know are safe. Don't share data outside unless you're allowed to, follow IRB procedures, etc. So in terms of the future of AI in healthcare, I would say that having optimized, efficient, and reliable models will improve patient outcomes. So I encourage it and encourage you to take a look at the Raytune code that we're providing. And if you need help getting it started or running it on the CHPC, I recommend that you reach out to me and I'll be happy to sit down and explain this to you in detail. But that's it for the seminar. Are there any questions from the audience? Feel free to unmute and ask your question.
Yeah, so I've had some experience doing some of this, hyperparameter optimization in the past. I mean, what's your feeling about the the time it takes to do hyperparameter optimization versus using those same cycles just to have a slightly longer training time.
So I would say that training for a longer period of time will ideally reduce the loss, considering you have a decent set of hyperparameters. However, I would note that you'll get a lower loss still if you have an optimal set of hyperparameters to work with. But there's kind of a ridge of hyperparameters that are optimal for a given problem. So there's not typically a true global minimum. There's kind of a set of hyperparameters that form a ridge that would work well. So, I mean, if you are very good at doing this yourself, if you have a good sense of how the models improve by varying the different hyperparameters, you can probably pick a good set of hyperparameters and then just train for a longer period of time. But if you want to be fairly exhaustive and pick something, if you don't have any real knowledge of how this model behaves, so if you're a fairly naive trainer, then I would recommend utilizing something like Raytune with an exhaustive hyperparameter search using Bayesian optimization. Are there any other questions from the audience?
Hi, I have a question. If we want to apply Bayesian optimization, where can we define this in the Raytune structure?
So you would define that when you're actually setting up the tune parameters. So it's here within the tuner space. So this is just a snippet of the code. I'll provide the full code and you can take a look, but it would be when you're setting up the parameters. Actually, let me see if I can just pull up the code here and I'll show you specifically. So here I'm defining the search algorithm. So this is utilizing Optuna search. However,
Oh,
you can,
I'm seeing the other screen.
okay. So here within my code, I'm defining the search algorithm here. So you could utilize whichever search algorithm would be supported. So you can do an exhaustive search, or you could utilize a random search or Bayesian-based optimization. So this is where you would actually define it. But this code will be on GitHub shortly after the seminar, and you can feel free to try it on the CHPC. Now, it just takes a while to actually complete. But if you want, we can sit down together and we can go over this code and how you can best utilize it.
Okay, thank you.
Are there any other questions from the audience? All right. Well, if not, thank you all very much for attending, and the code will be in the GitHub shortly after this. Feel free to reach out to me via email if you have any specific questions or you'd like to use this code, and we can set up a session to walk you through how best to utilize it for your own problems. My email is dennist@wustl.edu. Thank you. Have a good day.